Hi friends, today we start optimization tutorial 17. Today I'm going to look at the three different conjugate gradient methods. Specifically, we are going to address the problem of quadratic functions, and it's very important to figure out conjugate gradient methods in the context of quadratic functions because in fact if you look at the derivation of these methods, they are based on quadratic functions. So we are going to show this today using Python programs. I am Dr. Ganguly. Now in today's tutorial we are going to cover three different conjugate gradient methods. These are Fletcher-Reeves, Hestenes-Stiefel and Polak-Ribiere. We have discussed these methods before also in the previous tutorials, and today we are going to look at only quadratic function situations. Now you know that when you go through direct search in the design space, you essentially move with the algorithm xk plus 1 equals xk plus alpha k dk, and here dk is the search direction, which is given as minus ck plus beta k dk minus 1 in the conjugate gradient methods. And what happens is that beta k is different for each of the three different formulas given here, and we have minus ck in all these situations. So essentially what the conjugate gradient method does is that it deflects the steepest descent search direction, which is negative of the gradient vector, by this quantity here, which is beta k into dk minus 1. Now you can look at optimization lecture 17 for the complete derivations of what are conjugate gradients, what is the conjugate gradient method for quadratic function, and so on. And today I'm only going to use some of the formulas we have derived in that particular lecture and some of the theories we have obtained. And we are going to illustrate using Python code how this works for some simple quadratic functions. Let us briefly review the conjugate gradient method in its general form. So when you are going to start this method off, you do not have access to the point k minus 1, which is required here, for example, dk minus 1. So what you do is that when k is 0, you simply use the steepest descent search direction. So you set d0 is minus c0. And of course, you assume that x0 is given. That's the starting point which you require in gradient search methods. Then you move in the design space using this formula here. Xk plus 1 is xk plus alpha k dk. And each time you can then calculate dk using this formula, because once k is 0 has been calculated, the remaining time you have access to the previous design vector and so on. Now let us look at the three different formulas for these popular conjugate gradient methods. So in these formulas, the difference is in this beta k. Remember, beta k is a scalar value. For the Fletcher-Reeves, you have the definition given by norm of ck divided by norm of ck minus 1 square. And this essential equation is basically the same as ck transpose ck, and this denominated term is ck minus 1 transpose ck minus 1. So we can calculate it using this formula or using this formula. In this particular course, I'm going to use this formula most of the time because it's simply the dot product of these two vectors. And if we write the Fletcher-Reeves in this manner, you will see some of the similarities with the Polak-Ribiere method and also with the Hestenes-Stiefel method. So if you look at the difference between Fletcher-Reeves and Polak-Ribiere, you will see that there is an extra term present in this second method, and that involves the ck minus 1 term here. And if you look at the Hestenes-Stiefel formula, which is probably the most complicated, you also have the presence of dk minus 1 term here, and you certainly have these two ck minus 1 being present here. So there is a little bit of difference in these formulas. Their derivations are different. I have given their derivations in lecture 17 and lecture 18. You can check them out if you're interested. Now, of course, you will see that in Fletcher-Reeves, this particular value is always going to be positive because this is something which is the norm square. But in the case of the remaining two methods, what can happen is that beta k could become negative, and it's generally suggested that a beta k value which is positive is more preferable. So what people do is that they set beta k is max of 0 or beta k here. So what's going to happen is that you are going to basically take the value 0 if you have a negative number here. Now this essentially means that you are setting it back to the steepest descent search direction. So that's something to keep in mind. Now what happens with quadratic functions? When you have a quadratic function of this form, what happens is that you have a specific derivation or an explicit formula for alpha k, and this I have shown in lecture 17. You can check it out. Alpha k can be calculated as negative dk transpose ck divided by dk transpose a dk. Of course, you know dk is the search direction at point k, ck is the gradient vector at point k, and alpha k is the step size. So in this case we have a closed form solution for the step size. Now one of the limitations or requirement for this particular method is that A should be a symmetric and positive definite matrix. So we need to check that out. And one thing which will happen if you use this particular alpha k value is that if you have a multivariate function with n dimensions, then you are going to converge in precisely n iterations. So that is something which is coming out of this particular conjugate gradient theory. Again, I have proved that in lecture 17. You can check it out. I'm going to leave it in the end screen and also in the description box, the link to the particular video. So now what we are going to do is we are going to write a Python program for the conjugate gradient method for quadratic functions. And we are going to show that for this particular function, which is a function in 3 dimensions, that is n equal to 3, this should converge in exactly 3 iterations with all the 3 conjugate gradient methods, because this of course you can see is a quadratic function, and you also see that this is a function where the A matrix is going to be symmetric, it's going to be positive definite, and we are going to start this optimization process from 5, -5 and 5. So let us start building up the computer program. So we start by defining the function f of x and the gradient vector. So the function of f of x is simply x1 square plus 2x2 square plus 3x3 square defined here. And then we have the gradient vector. Now you can clearly see gradient vector will be 2x1, 4x2 and 6x3. So essentially these are the partial derivatives of f with respect to x1, x2 and x3 respectively. So I have then coded this gradient vector here. Now of course you know in Python the vectors start from 0. So here you are starting from 1. So you have 1, 2, 3, but in Python you have 0, 1, 2. Now let's look at the A matrix. Of course, if we look at this function here and we compare it to the generalized quadratic function here, we can very easily see that the A matrix is going to be a diagonal matrix with 2, 4 and 6. So remember that when you have this kind of quadratic form, you can express A as a symmetric matrix, and also if you remember, then A is going to be the Hessian matrix for this particular function, which you can obtain here by taking the second derivative of f with respect to these different variables. And of course, you are going to get this particular matrix here. Now we introduce a simple function here which is going to check the matrix A, and this is more for figuring out some of the things in Python and also realizing that you need to put in some kind of checks in your computer program every now and then. So we call this function as A matrix and we feed in the matrix here. And what this function does is that it first checks whether the matrix and its transpose are equal. And if so, it's going to return true. If not, it's going to return false. Then it checks if the matrix itself is positive definite. Now positive definiteness would require that all the eigenvalues would be greater than 0. So that's what it's checking here. And here I am using some of the built-in functions which are present in Python and which are present in NumPy. Basically remember, NumPy is something which is very powerful, and in many programs, for example in C, in Fortran, C++, you may have to write your own code to do some of these things, but in Python you can invoke NumPy and get a lot of these things done for you. Now what we do is that we check the situation that if both these situations are true, that is it is symmetric and positive definite, then I say ISIM is true and return this. And if both these are not true, then I basically return ISIM is false. So this is going to help me check the situation whether A matrix is positive definite and symmetric or not. Now let's write each of the three different functions for the three conjugate gradient methods. So I first start with the Fletcher-Reeves function, and the Fletcher-Reeves function essentially takes in the value x, that is the starting value x0, tolerance is a small number, max is the dimension here I use in the for loop, and I also need to send in the A matrix here because that's going to help me calculate the alpha or the step size. So then I have this for loop here. I start off with the gradient vector definition, and then when I is 0, I use the steepest descent method, which is d is minus c. I then use the fact that beta is essentially the dot product of c and c divided by the dot product of ck minus 1, ck minus 1. Then I update the search direction as negative c plus beta into d old. So remember dk minus 1 is d old here. And then I calculate alpha using the formula here, which is there for search direction for quadratic method for the conjugate gradient type method. So again, this is negative dkt ck. Again, I can simply get this using the numpy dot product. And in the denominator, I have the dot product of a into d and d itself, and there is a negative sign here, so this is going to give me alpha. Then I update x as x plus alpha d, which is essentially this last piece of equation here. Now remember, I'm storing the c vector and the d vector in this d old and c old, so these correspond to the dk minus 1 and the ck minus 1 vectors respectively. Finally, I have this breakout if statement that if my gradient vector becomes smaller than tolerance, the norm of the gradient vector, then I will break out of the for loop, else I will continue doing this thing here. And finally, I'm going to return the optimal solution x and the number of iterations it took to converge. Remember, in Python, I is going to start from 0, so we need to keep that in mind. Now we essentially take the same function and rewrite it very slightly for the Polak-Ribiere method. So here the difference is primarily in this beta k value. You see the beta function is slightly different, or the beta code. So here I have to use the fact that I have the dot product of c minus ck minus 1, which is c minus c old and c. And in the denominator, I have the dot product of c old and c old, which is ck minus 1 and ck minus 1. Now, for this particular method, there is the possibility beta may go negative, so I plan for that. If beta goes negative, I simply said beta is 0, which is I go back to the steepest descent method here. I basically restart the conjugate gradient method here. And of course, I have the same formula for alpha here, and then you can break out of this if the norm of the gradient vector is below tolerance. So that's something to keep in mind. Finally, this Polak function also returns to me x and I. Finally, I have the Hestenes-Stiefel function. Here, the main difference is again going to be in the beta calculation. So you see this formula in green is given here, which I have written out here. So here you have the dot product of c minus c old, which is given here, and c here. And in the denominator, you have the dot product of c minus c old and d old. So these are all vectors which are present with us. And again, I put in the condition that if beta becomes less than 0, I will set beta to 0. And then I update the search direction as minus c plus beta into d old, which is this formula. Again, the same formula for alpha can be used, which is defined for the quadratic function, that is negative dk transpose ck, dk transpose a dk. Remember, the matrix A is coming into these functions through the argument list. Finally, I have d old is d, c old is c, and then I check for the norm of the gradient vector here. Keep doing the for loop till I converge, and once I converge, I return x and I. X is the optimal value, hopefully, and I is the number of rounds it took to converge. Let us now invoke all these functions in a main program. So in the main program, I'm first going to import numpy as np because I'm using numpy so many times. I give the tolerance as a small number, which we use essentially to converge for the norm of the gradient vector. I give max as 1000 for the for loops, which I'm using in all those conjugate gradient function. I define the starting point x0 as a vector of size 3, that is 5 minus 5, 5, as defined here in this math notation. And I also defined the A matrix as a matrix here, which is essentially 2 0 0 0 4 0 0 0 6. So that's coded in here. Now at this point, I call that particular function, which is A matrix A mat, and that's going to give me back the particular value, it is true or not. So if A is symmetric and positive definite, I'm going to get true. If not, I'm going to get false. Then I use this fact here. If this particular statement is true, that is A is symmetric and positive definite, then I call these three functions here and I get the solutions for Fletcher-Reeves, Polak-Ribiere and Hestenes-Stiefel. And each time I print out the optimal value, which is given by these particular functions. And also I am going to print out the value of k plus 1. Now remember, since Python starts the index I in those for loops from 0, I have to put a plus 1 here. So that's going to make sure that I get a reasonable natural number here, which corresponds to the actual number of rounds it took to converge. And so in case the matrix is symmetric and positive definite, I go through this part, and if it is not, then I simply print that A is not positive definite or symmetric. So these kind of if else statements help us make the code more robust, more realistic than if we just wrote it without thinking about it, because what happens is that there may be somebody who may use the wrong matrix here, and so we should actually tell this person that he is doing something wrongly rather than actually just run the code and give them some result. So let us look at the output. So essentially this is the input as far as x0 is concerned, 5 minus 5, 5, and what is printed out is that is A symmetric and positive definite. I get the answer as true. So since this is true, it goes into the if part of the statement and it gives me the output for these three different conjugate gradient methods. Now I can clearly see that each of these converges at 3 value, that is 3 rounds of the code, and essentially I also see the minimum point is 0, as you would expect in this particular case. So these numbers are printed out, but as far as mathematics is concerned, we can consider these to be 0. So essentially we see here that the fact that the conjugate gradient methods for quadratic function would converge in n iterations for an n-dimensional problem is actually being proved here for the value 3. So in this particular problem, n was 3 and the value we converged at is also 3. So these are working out very well in this case. Now let us just check the case where, let us say we input a matrix with a -6 here, which I have put here. So in this case, what would happen is that you of course know that eigenvalue is going to be -6 here. So this is not positive definite, though it is a symmetric matrix. So what happens here is that we again run the code and let's see what it tells us. So this time it tells us clearly that it's not true that A is symmetric and positive definite, because we saw though it was symmetric, it was not positive definite. So we get the false value here. And in this case, it is going to go through the else part of the particular code. And so I get the printout that A is not positive definite or symmetric. So we do not try the thing that we are not using the conjugate gradient methods here. We don't put the call to those different functions out there. So that's something to keep in mind. So since the matrix here is not positive definite, we don't bother about using that particular formula, because that formula for the direction we have for alpha k is actually valid for positive definite methods and so on, or positive definite matrix. So now for the homework problem, I would ask you to slightly increase the complexity of the problem to 4 dimensions. So let us define this function here as x1 square plus 2x2 square plus 3x3 square plus 4x4 square, and then start with a design like 5 minus 5, 5 minus 5, and then compile that particular program and run it. I am doing all this in Google Colab. You can also download Python. You can check out in Google how to download Python on your computer and use it. But Google Colab actually lets you do it on the internet itself. So that's something which is kind of useful. So of course, what should happen here is that you should converge at 4 value, and let's check that out if that is actually so. Please leave it in the comments to this particular video for all the 3 different conjugate gradient methods. So in today's lecture, we discussed a very important topic about how the conjugate gradient methods do for quadratic functions. Remember, these methods are actually derived for a quadratic function. So it's of course expected that they will work very well. And they did work very well for all the cases we considered. We are able to use the value of step size using this formula here. So that gives us a very nice closed form expression which we can use provided we have the matrix K. Of course, if you are using conjugate gradient or any method, we would have access to dk and ck, but access to A is required, and that's only going to be possible for quadratic functions because they can be written in this form: half xtax minus btx. Remember that you need to check that A is symmetric and positive definite, and then this thing will work out very well. And we also saw that there is this particular theorem which I have proved in lecture 17. And you can look at that lecture as to how this particular proof comes about, because it is a very interesting exercise in matrix theory in terms of the concepts such as conjugate gradients and so on. So actually, the gradients are conjugate with respect to this matrix A. So that's something to keep in mind. That's how the word conjugate gradient comes. Actually, we say that the two search directions are some directions which have A conjugacy. So look at lecture 17 for some of the details about that particular concept. I'm going to stop this lecture now, and in the next lecture, or rather I should say tutorial 18, we are going to unleash these 3 conjugate gradient methods on our general function, and we are again going to revert back to the classical algorithm or the classical step size method so that we can then solve those problems. Remember, this particular step size is valid for quadratic function. So if you are dealing with a more nonlinear function, dealing with general nonlinear function, you actually again have to resort to the numerical 1D search.